All right, so today is 4.1.2. We're talking probability of events. So the reason this is helpful to just understand at its basic level is when you're making choices in life, when you're taking risks, educated guesses and risks on what your options are, you want to know the basic probability of an event happening. So if you're always, creating life plans and life goals that are, hoping for the really low probable event, that's going to be a hard way to live. You got to make sure that you're balanced. You're taking educated risks or informed risks that also are informed by the probability of things happening and actually working out. Okay, so the goal is always to have as many options as you can to know the possible outcomes, if possible. So that's what probability is really about. The first board over here, and we have this example from the warm-up we'll use again. This is basically looking at the probability of different cards being drawn. Bless you. The left board here is for a single event. Okay, so that would be picking a card out of a deck. So we have a standard 52 card deck. Okay, we're going to do that. It would be rolling one die. You just roll one die one time, and it could be flipping a coin. Okay, so all these things, I think that logically we kind of know how they work, but we're going to figure out how to express it mathematically. So again, like Monday, it's just some notation we have to get used to. It's nothing too far-fetched from what we did Monday. So let's look and see. Here's our probability, basic probability for a single event. Formula we'll use. The probability of the event, E, is the number of outcomes in event E divided by the number of outcomes in the sample space. Sample space is all the options. Okay, so if I want to roll a multiple of 3 on a die, how many options do I have? What are the number of outcomes for that? Right? How many? So we have what? We have 3. We have 6. Okay. So there's 2 options. Yes. What are the total number of outcomes for the sample space? In a die, it's 1, 2, 3, 4, 5, 6, right? So how many options for rolling a multiple of 3? 2 out of the, divided by the number in the sample space, 6. 2 over 6 is 1/3. So I have a 1 in 3 chance of rolling a die and getting a multiple of 3. Okay, so looking at that, let me get rid of that for a second. Let's go ahead and look at the probability of rolling a club card. So the number of club cards, if you were thinking set theory, I might call this, set C on clubs. And we'd have, let me see, what do we have? We have the 1 of clubs, we have the 2 of clubs, 3 of clubs, 4 of clubs, 5 of clubs, 6 of clubs, 7 of clubs, 8 of clubs, 9 of clubs, 10 of clubs, Jack of clubs, Queen of clubs, King of clubs, Ace of clubs. Those are all the options in the set. If I was expressing that using our table we have up here, then I would go ahead and in the clubs, go ahead and do all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yes?
I don't think there's a 1 of clubs.
There is not a 1 of clubs.
There's, yeah.
Starburst coming your way after the film. Yes. Mistakes are always rewarded. Correcting my mistakes.
Okay, now I'm going to start.
Not in general. All right. Ace is the one, really, but we'll put it here. So how many options do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And I know that too from doing it in table form here instead of in notation, set notation. Here, table form, we have 13, so we're going to put that in here. 13 out of the total number of cards, 52 cards. Okay, 52 cards. 13 over 52 reduces to what?
0.25.
1/4.
This is 0.25.
0.25.
Which is 25%.
Which is 25%. You're going to have to do it in decimal percent and fraction. So just get used to that. If you have that example there, that'll probably remind you pretty well. So 1 divided by 4 is 0.25. 25 cents is 25%. Just think of it as money. It's really easy. Okay. So let's go ahead and do the probability of drawing a face card now.
You already got that one.
We did that in the warm-up, so we'll do that pretty quick here. All the face cards, Jack, Queen, King.
So we're Jack.
How many do we have here?
12.
12 out of 52 total in the deck. 12. So 12 divided by 52, look, we can go 6 over 26, 3 over 13. 3 divided by 13 is
23.1.
so
0.23. I think that's
231.
think that's
So it's
right.
23.1%.
yeah. That's how I remember.
All right, which is more likely?
Clubs.
Club. Okay. And there are some overlaps, but I'm just talking about one event. I'm drawing one card. Okay. I'm not talking about this and this happening. If there were two conditions on it, then it would be in the next board. It'd be a multiple event situation. Let's see. We're going to get the clubs or a face card, or both. Let's see. Clubs. All right. So the clubs were 25%. The face card was 23.1%. So if I was weighing which choice to make, clubs was the correct choice. So we got it. We got it. All right. Shoot. Everything still works in the world. That's great. All right. This is the other breakdown. Probability is just on a scale from 0 to 1. Okay. 0 is never happening. It's 0% chance. A 1 is 100% happening. It's always going to happen. Your probability is always going to end up coming in some kind of fraction, which then we could divide out to get a decimal and get your percent from it. If you forget how decimals and percents work, think of 1/2. Because we could think of 1/2, that's 50%, right? That's easiest to think of. 1/2 is 50%. It's 50 cents, 0.5. So use that example. If you get confused with that, it's going to be helpful to do it. Okay, so let's go ahead and looking over here. This is for multiple events. Okay, events that are connected. So let's go ahead and do that for, I'll give you a minute just to get that jotted down quick. I'll pause it. All right, now we're talking about multiple events or connected disjointed events. And this is where there's two events happening, or it's also, there's two conditions where there might be some overlap. The overlap part is the hardest part for the lesson. So let's kind of take it slow here. The addition rule is the main rule here for probability. We're going to have the addition rule. Next week we'll have the multiplication rule. So those are the main two that we're going to be dealing with. So today for the addition rule, when we have an OR type event, we have disjointed events. Disjointed events that are mutually exclusive. So if I'm looking back over here for the drawing the card, a mutually exclusive event would be I'm going to draw a spade or a diamond. There's no overlap, right? The probability is just going to be all the options that are spades or all the options that are diamonds. Okay. So they're mutually exclusive. They're disjointed because there's nothing that those two conditions have in common. And in that case, then, all we have to do is to find the probability included in set A and set B. We just find the probability of one of them and the other one, and we just add those together. Yes. Yes. No problem. So this is really basic here. If I was doing the probability of drawing a spade would be 13 out of 52. Drawing a diamond would be 13 out of 52. If you think about that, if we're just kind of filling in the blanks here, to draw a spade would be, here's my 13 here. Drawing a diamond, here's my 13. I'm just going to do that. Okay. So there's nothing that overlaps. If I was saying, what is the probability of drawing a spade or a diamond, then it would just be 26 out of 52. which is a 50% chance. Does it make 50% chance make sense to you? Because I have half of the options, right? Half of the options. Okay. So going back over here, the next little step. The next little step is when we have connected events. So my connected event that we're going to do in the example problem is it's an even card or it's a diamond. Is that going to have some that have things in common? Think about that. It's an even number.
No.
And it's a diamond. No?
No.
Yeah.
Let's see. Let's see. So we have even numbers. 2, 2, 2, 2, 4, 4, 4, 4. So what do you think now, Isaac? Change your...
Oh, I thought you mean like even cards like they're excluding the intersection with even diamonds.
Right.
Excluding even diamonds.
Right, so that's actually the big picture. I think you were just answering the big picture before the small question. So that's good, you're ahead of us, that's always good. The probability of even plus the probability of drawing a diamond. So let's see what we get. 1, 2, 3, 5. Now, let's look at that over here again. So I just filled in all of the even cards, all of the diamonds. If I was counting the options, or the probability of having this happen, an even card or a diamond, if I go in and count in all my evens, how many are there? 5 times 4, rows and columns, you have 20. Diamonds, I have 13. So is the probability of drawing a diamond or an even, let's see, what would that be? 20 plus 13, 33 out of 52. Is that right? $33 out of 52. What do you think? Yeah, if you have an idea on that. First, just is that right or wrong? The 10 of diamonds has been counted in both of those groups. That's an issue. We can't count the card twice in this way. Okay, so 33 out of 52 is actually incorrect. Let me give you another analogy here. If you worked for the city and you were paving, let's say this is Stockton, right? And then we have another road here. This is Fruit Ridge. Okay. If I said I want you to buy the exact amount of cement that you need to pave these two roads, I need you to buy the exact amount. And you go through and you say, well, I'm going to pave all of Fruit Ridge first. You pave all of Fruit Ridge. Then you start to pave Stockton. Your machine gets to right here, and what do you notice? It's what? Okay, then what'd you say?
You can't pave it over again.
Right, it's already been paved right here, right? If we're paving just Fruit Ridge and Stockton, when we get to an intersection, right? When we get to the intersection, we aren't going to pave the little intersection twice. It's already been paved on Fruit Ridge, so then we continue on the other side. The same exact idea works with this, where we have diamonds and evens, and these we're not going to count twice as far as our number of options. We need to subtract out the intersection. Okay, just like if you're paving the street, I wouldn't pave this twice over where it's like a big bump and it gets bigger. I would pave until the intersection, and then I would stop and go to the other side. So let's see what happens here. What is the probability of drawing an even card? How many do we have? 5 times 4, so we had 20. We had 20 out of 52. All right. What is the probability of drawing a diamond? How many do we have?
13.
13 out of 52. 13. Okay. The key for this is this last part. I add together the probability of drawing an even card and a diamond, but I need to subtract, what's this symbol mean again?
The intersection line.
The intersection. I need to subtract out the intersection that are in common between these. Just like paving the road, you don't want to pave over the road twice. We don't want to count those cards twice. So how many did we have in common over there? 5. Minus 5 over 52. Let's see, this is 33 minus 5, 28 out of 52, which gets us to 14 over 26. That gets us to 7/13. That gets us to 7 divided by 13 is 0.538, which is 53.8%. Some of these problems are going to have you put it in the fraction, decimal, and percent. It's no big deal. 7 divided by 13, decimal, move it twice, percent. That's all we have to do. So I'm going to do one more with you here. And actually, this one is very similar to what we did, so let's go with I'm going to do this. Hopefully this hits. All right. So let's say that we have the option where we're looking for the probability of an even card or a king, and I'm going to rewrite this union. Okay, so the probability of both of those together, and that's equal to the even card probability plus the probability of the king, and then any intersections from the king and the even card. So let's go back over here. Actually, we'll keep all the evens because we did that already. Is there a question in the back? Questions are fine. All right, here's all the even cards. Here's all the evens. I need to now do all the kings. All right, so how many cards fit into the set of even cards? So what are the cards that fit into that? Let's see. It's all the different suits, and 2, 4, 6, 8, 10, and 20. So we have 20. 20 over 52, just like before. What's the probability of getting a king? How many options are we looking for?
4.
4 out of 52. Now we need to minus the intersection of evens and kings. Do we have any intersections?
1.
Where?
Oh, no. Yeah, no, we don't.
Right? So these are exclusive events. These are the evens. Here's the king. There's nothing overlapping.
This is 24.
So this is where we're going to have 0. Okay. So even if you forget if it's a disjointed or a connected event, you can just do the addition property over here, because the overlap is sometimes going to be 0 if it's mutually exclusive. So you might even figure it out that it's mutually exclusive that way. Sleepy. The time change is killing you guys. 26 out of 52. It's 1/2. 0.5. 50%. Who gets that starburst? Me.
He gets all the
I
Starburst.
think so.
He gets all-
26. Let's see. 6 over 13. 6 divided by 13 is 2. 462.
Yeah.
All right, then we'll go 46.2%. Got it? Hey. So this is if we have an event, even if we deal with it with the addition property, the overlap, if there's no overlap, there's no overlap. Okay, so if there's no overlap, it's going to be minus 0. All right. Tell you guys are enthused today. Ironic.
Publicly admitted.
All right. No big deal. It's Wednesday. All right, 123rd gets a package of Oreos. Don't forget to subscribe. Don't unsubscribe and subscribe. Just subscribe. That's it.